At the edge of the largest empty regions in the universe, galaxies do not fade out gradually. They simply stop. The universe, on its largest scales, is not uniform. Matter is not spread evenly across space. Instead, it clusters into an enormous web, long filaments of galaxies, dense nodes where filaments intersect, and vast hollow regions between them. These hollow regions are called cosmic voids. Voids are not small. Some span hundreds of millions of light-years across. They contain almost no visible matter, no galaxy clusters, very little gas detectable at radio wavelengths. The web of structure that defines the observable universe wraps around them like foam wraps around air pockets. Between a void's interior and the dense filaments that border it, there is a transition zone, a boundary region. Under the models that currently describe how large-scale structure forms, this boundary should have a predictable character. As you move from the edge of a void outward toward a filament, galaxy density should rise gradually. Slowly at first, then more steeply as gravity pulls matter into threads and nodes. The change should be smooth, measurable at every step. That gradient is how the universe organizes itself under gravity and expansion working together across billions of years. It is the expected behavior of structure at the largest scales we can map. When astronomers began mapping the precise edges of very large voids, not the interiors but the boundaries, something in the data did not match. Galaxy counts approaching the boundary do not rise gradually. In some regions, the density rises at a rate that current formation models do not predict well. More significantly, in targeted surveys of specific void boundaries, the fall-off on the void side is sharper than it should be. Galaxies appear to be present, and then, within a distance that is cosmologically short, they are not. The transition is compressed. The gradient that should be stretched across tens of millions of light-years appears to occur across a fraction of that distance. This is not a measurement artifact easily dismissed. Multiple independent surveys using different instruments and survey methods have identified similar compression at void boundaries. The sharpness is not uniform across all voids. Some boundaries behave roughly as expected. Others do not. The cutoff is real. A cosmic boundary where structure suddenly thins out, not because gravity has had less time to work there, not because matter was never present, but for a reason the current standard model of structure formation cannot cleanly account for. The question that follows is not simple. What is enforcing this edge? To understand why a sharp boundary is anomalous, it helps to understand what sets void edges under the standard model. Cosmic voids grow. In the early universe, small underdensities, regions with slightly less matter than average, expanded faster than their surroundings. As dark energy accelerated the expansion of space overall, void interiors emptied further. Matter drained toward the walls. Gravity pulled what remained in the filaments and sheets into denser concentrations. The void grew larger. Its boundary moved outward. This process is gradual. There is no known mechanism in standard cosmology that would create a sharp cutoff. No wall, no transition line, no force that specifically repels or stops matter at a precise radial distance from a void's center. The boundary is a statistical feature, a region where the probability of finding a galaxy drops, not a physical surface. Evidence gap mode applies here because the core problem is not a theoretical contradiction. It is a missing explanation. The observation exists. The data is real. What is absent is any identified mechanism that could produce the sharpness observed. Before examining the candidate explanations, it is worth establishing precisely what the evidence gap means in this context. A gap in evidence is not the same as a gap in imagination. Theorists have produced multiple frameworks capable of generating sharper void boundaries under specific conditions. The problem is that none of those conditions can be confirmed with current data. The gap is not between possibility and observation. It is between observation and the ability to verify which possibility is operative. That distinction matters. It means the anomaly is not unsolvable in principle. It is currently unsolvable in practice, and the distance between those two states is not closing quickly. One line of investigation focuses on dark energy. The current standard model treats dark energy as a uniform field, a constant energy density filling all of space equally, driving expansion everywhere at the same rate. But some models propose that dark energy may not be perfectly uniform. If the energy density of dark energy varies slightly from region to region, the expansion rate would vary correspondingly. Near void boundaries, a locally higher dark energy density could push matter outward more aggressively, stripping the boundary zone faster than the standard model predicts and sharpening the cutoff. This explanation has not been confirmed. The variation in dark energy density required to produce the observed sharpness would be small, potentially below what current surveys can resolve. So the absence of confirmed evidence is not the same as evidence against it. The data gap is real, and it is constraining. The dark energy density variation hypothesis carries a compounding problem. To test it directly, researchers would need to measure the expansion rate of space at sub-void scales, not the average expansion rate of the universe, but the local rate in the transition zone between void interior and surrounding filament. No instrument currently operating can resolve expansion rate variations at the spatial precision that test would require. The measurement is theoretically possible. It is not currently achievable. The gap is not a question of missing data from one survey. It is a question of instrument capability that does not yet exist. A second line focuses on dark matter distribution. Galaxy formation traces dark matter. Galaxies form and persist where dark matter halos provide the gravitational scaffolding for gas to collapse into stars. If the dark matter distribution at void edges is itself sharper than expected, if dark matter halos thin out more abruptly than models predict, galaxies would follow. The observable cutoff in galaxy counts would reflect an underlying cutoff in the dark matter structure. The problem is measurement. Dark matter at void boundaries cannot be directly observed. Its distribution is inferred from the galaxies it hosts and from weak gravitational lensing, the slight bending of light from distant sources as it passes through dark matter concentrations. At the scale of individual void boundaries, the lensing signal is weak. The statistical power needed to map dark matter structure at this precision requires survey volumes and depths that current instruments only partially cover. There is no confirmed dark matter density profile at void boundaries that resolves this. Even the galaxy counts themselves introduce a layer of uncertainty. Galaxies observed at the boundary zone are not uniformly visible. Smaller, dimmer galaxies, the most numerous type, fall below detection thresholds at the distances involved. What surveys record as a sharp cutoff in galaxy counts may partly reflect a sharp cutoff in detectable galaxies, not all galaxies. Correcting for this incompleteness requires assumptions about the galaxy luminosity function in these environments. Those assumptions are uncertain, and they affect the inferred sharpness of the boundary. The anomaly may be slightly overstated. It may also be slightly understated. The direction of the correction is not definitively resolved. A third possibility involves what are called void exclusion effects, statistical features of how voids are identified and how their edges are defined algorithmically in survey data. If the definition of a void boundary introduces a systematic compression in how the surrounding density is measured, the sharpness may be partly an artifact of methodology rather than a purely physical feature. This cannot be ruled out. But it cannot account for the full signal either. Cross-checks using different void-finding algorithms on the same survey data consistently reproduce a boundary sharpness above what the standard model predicts. The methodology explanation reduces the anomaly. It does not eliminate it. What the three lines of investigation share is an absence of data at the critical scale. Not a shortage of observations in general. The modern era of galaxy surveys has produced enormous catalogs, but a shortage of the specific kind of observation needed to distinguish between these explanations. High-resolution mapping of dark matter structure across individual void boundaries. Precise measurements of expansion rate variation at sub-void scales. Resolved density profiles that do not depend on galaxy counts alone. None of these measurements currently exist at sufficient precision. The surveys needed to produce them are either underway, planned, or require instrumentation not yet deployed. Euclid, launched in 2023, and the Vera Rubin Observatory beginning full science operations in the mid-2020s will both deliver the survey depth and sky coverage that void boundary analysis requires. Whether those datasets will sharpen the anomaly, soften it, or eliminate it remains unknown. The data does not yet exist. Until it does, the three candidate explanations remain equally plausible and equally unconfirmed. The boundary is observed. The sharpness is documented. The cause remains unassigned. The evidence gap at void boundaries is not a temporary problem waiting for the next instrument. It reflects a deeper measurement challenge. Void boundaries exist at scales where the survey volumes needed to resolve individual boundary profiles are enormous. A single void can span 200 million light-years. Mapping its boundary at sufficient resolution requires uniform, deep galaxy surveys covering thousands of square degrees of sky. Those surveys exist in partial form. They do not yet cover the full parameter space needed. Dark matter mapping via weak lensing loses precision exactly where it is needed most. In low-density regions where the lensing signal is faint and sparse galaxies provide few background sources. The void boundary is the worst-case environment for this technique. Models that predict void boundary profiles are sensitive to inputs that are themselves uncertain. The equation of state of dark energy, whether it is truly constant or varies slightly, changes the predicted boundary sharpness. The power spectrum of initial density fluctuations shapes how voids grow. Small uncertainties in these parameters propagate into large uncertainties in predicted boundary structure. No measurement currently available can break the degeneracy between these explanations. What cannot be confirmed, whether the unknown force driving the boundary gradient is a property of dark energy, a feature of dark matter distribution, or a combination of both. What cannot be measured, the dark matter density profile at void boundaries with sufficient resolution to test the competing models. What cannot be ruled out, the possibility that something in the physics of void growth is missing from the standard model entirely. The boundary exists. Its cause does not yet have a name. The sharpest void boundaries in the observable universe sit at the intersection of everything uncertain in modern cosmology. Dark energy, dark matter, the growth of structure, all three are invoked to explain what is seen, and none of three can be tested precisely enough at these locations to produce a verdict. Future surveys, wider, deeper, more uniform, may resolve the dark matter distribution at void edges well enough to distinguish between the explanations. Or they may sharpen the anomaly further, revealing that the boundary behavior exceeds what any current combination of dark energy and dark matter models can produce. Both outcomes are possible. The universe draws edges in the distribution of its own matter at scales no human intuition can hold, for reasons that may require physics not yet written. The boundary is there. What enforces it is not known.